Today, let us discuss one of the key topics of mechanics, that is center of mass. Center of mass is one of the important topics in mechanics. If you are thorough with this topic, most of the doubts in rotational motion and other topics also will be cleared easily. Before going into the topic, let me tell you something regarding the way we approach the topic. By the time we complete this chapter, our goal is to know what is center of mass, how to define center of mass, and how to do problems related to center of mass, and how to apply the concept of center of mass in various other aspects. First, let us go for the definition of center of mass. Definition of center of mass: it is the point which will represent which represents motion of the whole body and also it is the point where total mass of the body is supposed to be concentrated. So this is the basic definition of center of mass. Even though it appears to be simple, in many complicated situations you can come out of it simply by knowing the definition. That's why in physics it is always essential to know the basic definition and true meaning of it. So here also, center of mass is basically the point where the total mass is supposed to be concentrated or appear to be concentrated. Let me give you one more example. To understand this definition, let us go for one example. Suppose there is a particle of mass 10 kg. There is a particle of mass 10 kg on which let us apply a force F is equal to 100 newtons. On a particle of mass 10 kg, we are applying a force 100 newtons. Then from Newton's second law, you know that acceleration of the particle is F by m, that is equal to 100 by 10. So 10 meters per second square is the acceleration of the body. Here, this particle will have acceleration 10 meters per second square. That is known to everyone. Now let us take a uniform bar of mass 10 kg, and let us apply a force F is equal to 100 newtons on this body. Wherever you want. It may be applied anywhere on the body. At any point on the body you can apply the force. When we apply this force F equal to 100 newtons on this body, different particles may move differently. Suppose this part will move like this part will move like this. But there is a point in the body which will have the acceleration exactly equal to F by m, that is equal to 10 meters per second square. That point is center of mass. So the whole mass of the body is 10 kg, but acceleration of center of mass is 10 meters per second square. That means you can easily see the center of mass is representing the total motion of the body. So that's why we always say that center of mass is a point where the total mass appears to be concentrated. Now let us go further and explore this topic which is very interesting and easy. Let us approach this in a different way rather than which is given in books. Suppose there are two bodies, one is larger and another is smaller. Two bodies we have selected whose masses are different. One is huge, another is small. Now, where you expect the center of mass of these two bodies to be? Naturally, it should be nearer to the larger body. Somewhere here it should be. More massive this is, more nearer will be the center of mass. Less massive the object is, more farther will be the center of mass. So, in other words, we can have a relation that mass is inversely proportional to distance of center of mass. If there are two bodies, one is large and another is small, center of mass is located nearer to the larger body, means mathematically that can be represented as mass is inversely proportional to distance from the center of mass. Now, from this we can write mr is equal to constant. mr is equal to constant. From this we can also write m1 r1 is equal to m2 r2. So, this is a very good relation or very useful relation in center of mass. I am using it very frequently and you will find it more interesting to know this relation. Now, m1 r1 is equal to m2 r2 is the relation which goes further in this topic. See, suppose there are two masses m1, m2, there are two masses separated by a distance d. We are exploring the applications of this simple relation. There are two masses m1 and m2 separated by a distance d. Let the center of mass be at a distance x from m1. Let the center of mass be at a distance x from m1. Then automatically it will be at a distance d minus x from m2. It will be at a distance d minus x from m2. Now, by this relation we can write m1 r1 equal to m2 r2. That means m1 into x is equal to m2 into d minus x. Or you can also write m1x plus m2x is equal to m2d, or x is equal to m2d by m1 plus m2. So, distance of center of mass from m1 will be equal to m2d by m1 plus m2. This relation we got from this only. If you want the distance from m2, it will be m1d by m1 plus m2. As simple as that. So, this is one example where we used this relation. Let us go for another one. Suppose this is x-axis, this is x-axis, this is origin. A particle of mass m1 is here, a particle of mass m2 is here. m1, m2 are on the x-axis. Let the coordinate of m1 be x1, coordinate of m2 will be x2. Now, let the center of mass be here somewhere, whose coordinate is x. Center of mass has a coordinate x, this m1 has coordinate x1, m2 has coordinate x2. Now, let us apply the same relation m1 r1 equal to m2 r2 here also. This is center of mass of m1 and m2, no? So, this would be the distance of center of mass from m1 and this would be the distance of center of mass from m2. That means, this is equal to x minus x1. This distance is equal to x minus x1. Similarly, this distance is equal to x2 minus x. You can see this clearly. this distance is equal to x2 minus x. Therefore, m1 is at a distance x minus x1 from center of mass, m2 is at a distance x2 minus x from center of mass. By the same logic, m1 r1 equal to m2 r2, if you write m1 into x minus x1 is equal to m2 into x2 minus x. After further simplification, it will be like this: x into m1 plus m2 is equal to m1 x1 plus m2 x2, or x is equal to m1 x1 plus m2 x2 by m1 plus m2. So, from using the same relation, we are able to get the coordinate of center of mass in terms of coordinates of m1 and m2. So, this is also one of the applications of the same relation, m1 r1 is equal to m2 r2. Similarly, if the particles are on y axis, we can write y is equal to center of mass, y coordinate is equal to m1 y1 plus m2 y2 by m1 plus m2. Similarly, for z also we can write like this. So, see, we are using the same relation again and again, and we are getting almost solutions for each and every case using the formula m1 r1 is equal to m2 r2. Actually, it is the concept. Mass is inversely proportional to distance from center of mass. Now, if you extend this to any number of particles, so far we have seen that xcm is equal to m1 x1 plus m2 x2 by m1 plus m2. This is for two particle system. You can extend this to any number of particles with similarity. Suppose there are n particles, then center of mass coordinate will be equal to m1 x1 plus m2 x2 and so on mn xn by m1 plus m2 and so on up to mn. So, similarly, we can write for y coordinate of center of mass, z coordinate of center of mass. So, we have extended the two particle system to n particle system. This is generally written as, this can be written as sigma mi xi by sigma mi. So, x center of mass is this, y center of mass will be similarly be written in as sigma mi yi by sigma mi, and z center of mass will be equal to sigma mi zi by sigma mi. So, now we are able to find the center of mass to any number of particles without a problem using these relations. Again, we approached these derivations using the concept m1 r1 is equal to m2 r2. Now, let us do the same thing using another method.